Okay, so first of all, I would like to thank the organizers for this very stimulating conference week. And so in this talk, I'm going to talk about this disorder-induced transition, which is a bit less known than localization transitions, I think, namely the semimetal-metal transition. And I will show that in this case, the critical wave functions also exhibit multifractality. So I will start with some introduction on semimetal, so it will be a bit redundant with what Andre has presented, but I try to be brief. I will discuss the relativistic phases and discuss the effect of disorder. And then I will delve into the main subject, which is the computation of multifractality at the semimetal-metal transition. So I will define multifractality in this context. I will draw some comparison with Anderson localization. I will show how you can how multifractality dictates the behavior of the typical density of states, and I will present some explicit computation of the spectrum for general disorder. Okay, so introduction to semimetal. So I think that the most famous relativistic phase in condensed matter is graphene, which is a two-dimensional carbon honeycomb lattice. A simple tight-binding model for graphene takes into account nearest neighbor hoppings between the pz orbitals at each site. Additionally, you can add, of course, next nearest neighbor hopping, for instance. And Fourier transforming this Hamiltonian leads you to this kind of dispersion relation. So you see that the conduction and valence bands touch at the corners of the Brillaux zone, and you have two inequivalent points, touching points k and k prime. And moreover, these bands actually cross linearly near these points, which we call Dirac points, k and k prime. So if you do some linearization around for the Hamiltonian around k and k prime, you get a Hamiltonian of the form some Fermi velocity times the helicity operator, which is a pseudospin dot the wave vector k. And so you have the law in energy physics is then described by Y fermions, which are two components massless fermionic particles, and so you have a left-handed fermion, Y fermion at the k point, and right-handed fermions at the k prime point. An important consequence is that for half-filled graphene, that is for when the Fermi surface lies at the nodes, the density of states vanishes at the Fermi energy. So actually, three-dimensional materials can also host quasi-particle, relativistic quasi-particles, and these are called Weil or Dirac semimetals, depending on the number of bands that are crossing. In the case of Y semimetals, there are two bands crossing. So around each of these nodes, the Hamiltonian is exactly of the same form as for graphene, so it's a pseudospin sigma dot the wave vector k, except that here, of course, k is a three-dimensional vector. And because the flux of the Berry curvature over the whole Brillaux zone has to vanish, the Y nodes must always come in pairs of opposite chiralities. So material realization, so usually we classify the Y semimetals in terms of the symmetries that they break. They are either inversion symmetry breaking Y semimetals. This is the case of the first Y semimetals to be discovered experimentally, which is tantalum arsenide. Also, there are T-breaking Y semimetals that are predicted in magnetic materials, such as parachloroiridates, but they are not experimentally evidenced yet. The other case is Dirac semimetal. So in this case, you have four bands crossing linearly. So basically, you can think as a Dirac semimetal as two Y nodes pinned at the same crystal momentum of the Brillaux zone. And so these Dirac semimetals were also discovered very recently, for instance, in sodium bismuthide or cadmium arsenide. Okay, so this is the simplest picture for clean materials. Of course, real materials always contain some amounts of defects. So there are some defects that are very peculiar to two-dimensional materials. For instance, for graphene sheets, there are these ripples But for three-dimensional materials like Weiss metals, so you could think about defects due to impurities that are either charged or neutral, for instance, lattice defects, such as dislocations, or else vacancies, for instance. And so these defects will create some random potential V of R that we will treat as quenched, that is independent of time, and as a Gaussian potential with a zero average and with variance that I write as delta of the distance R. Okay, so these potential can be characterized by several things. First thing is its pseudo-spin structure. So the simplest case is a scalar disorder. That is a potential that is which is proportional to the identity operator in the pseudo-spin space. And so this is actually the type of disorder that controls criticality in three-dimensional Weiss metals. So I will only consider this type of disorder in the following of my presentation. There is also, you can think about a gauge field disorder, for instance. So in graphene, ripples actually create this type of disorder, gauge field disorder. And there is, so this is only for two-dimensional systems, not for 3D, you can have this random mass disorder. You can also characterize the potential by the correlation range of the variance. So there are, you can distinguish two regimes. The first regime is a short-range correlated potential. So imagine that the variance has some non-zero value only around some on a range of the size of psi d, which is the correlation length of disorder. Then when you approach the node, that is when the wavelength tends towards infinity, basically you can replace this function by some delta function of the position. Okay, so and I will write the corresponding disorder strength as delta s. The there is a further simplification that you can have. In the case of psi d much bigger than the inverse separation of the nodes in the Brillaux zone, you can actually neglect intervalley scattering. And this allows you to treat a single Y node. And this is the simplification that I will make in the rest of my presentation. The second case corresponds to long-range correlated disorder. So this is formally the case for psi d infinite. And typically, what you will have is a function that is a power law of the distance r, that is r power some exponent minus a, and I will write by delta L the corresponding disorder strength. And so this is not actually a purely academic situation, because lattice defects such as dislocations and unsquared charges are known to produce such disorder. So now we want to have discussion in which situation is disorder relevant, and to do that we can use some qualitative argument, which is basically a generalized high-risk criterion. So let's consider the variance of the potential integrated over a box whose size is the wavelength of an eigenstate, and divided by the square of the kinetic energy E. So basically you get the relative disorder strength, and the scaling as a function of the wavelength is the following. So it's lambda power minus d minus 2 for a bigger than d, and lambda power minus a minus 2 for a smaller than d. So we see that, especially in the case of a bigger than d, that is for mainly short-range correlations, this quantity vanishes in 3 dimensions, which suggests that disorder is an irrelevant perturbation. So what you get is that for weak disorder, you stay in the Weiss metal phase. But of course, for strong disorder, I mean, the general case would be that you get into another phase, which in this case would be a diffusive metal phase. So you will get, you will have a transition between these 2 points, and that crosses through a quantum critical point. A way to pinpoint this transition is to track the average density of states at the Fermi energy. So in the Weiss metal phase, it is 0, and then in above some critical disorder strength, delta star, it increases with a power law whose exponent is nu times d minus z, where nu is the famous correlation length exponent, and z is the dynamical exponent. So this is basically the exponent that gives you, that tells you how the dispersion relation is renormalized in the metal phase. This transition was first evidenced by Eduardo Fracklin for the simplest case, that is for scalar and short-range correlated disorder. Many analytical and numerical studies have been carried out since then. And so I just would like to present some values for the critical exponents nu and z. So analytical results on one loop, for instance, in 2 plus expansion gives nu equals 1 and z equals 1.5. And in numerics, well, there are different works, but this work, for instance, gives finds similar values, z and nu, of order 1.5. So you see that there's quite a good agreement for the dynamical exponent, z, but not so much for the correlation length exponent u, but this was discussed by Andre in the previous talk. These exponents are currently known at 4 loop in 2 plus epsilon dimensions, sorry. And better insight can be gained using other analytical techniques. For instance, you can use a non-linear sigma model, which is especially relevant to study, for instance, transport properties. You can map the problem to a gross Nova UKR model and treat it in 4 minus epsilon expansion, which is particularly interesting because it prevents high-order operators from being generated by the renormalization flow. Or you could also treat it using functional renormalization group, for instance. And so this brings me to the main motivations to study multifractality in this case. The first motivation, which is, well, on the theoretical ground, I would say, is that multifractality is a more complete and richer set of critical exponents to classify the transition. And on a more practical ground, it dictates the behavior of the moments of density of state, and especially of the typical density of state, which is quite easily accessible numerically. Okay, so you know that quantum interference due to scatterings and impurities can lead to this non-space filling wave function density map with these very sharp fluctuations, which is a hallmark of fractal structures. And these fractal features can be characterized by the moments of the wave function density. Actually, we define two moments. The first one is the inverse participation ratio, which is basically the power q of the wave function density integrated over the whole system size. And physically, the inverse participation ratio gives the moments of the inverse volume that is spanned by a wave function. But you can also define the participation ratio, which is defined in this way, and which represents the moments of the fraction of sites occupied by a wave function. Let's study the scalings of these moments, and especially I will focus on the participation ratio for 3 main cases. So for a localized eigenstate, you obtain that this integral is basically independent of the system size when the system size L is much bigger than the localization length. So you get the scaling law, which is L power minus dq minus 1. On the contrary, for an extended state, the two scalings compensate so that PQ is essentially independent of the system size. And what is particularly interesting is the case, of course, of critical eigenstates, where you have some non-trivial exponent delta q for the scaling law. And this exponent delta q is called the multifractal spectrum. So it is, in general, non-integer, hence the notion of fractality, and non-linear in Q, hence the multifractality, because each moment scales with its proper fractal dimension. Now, I just would like to give actually a more rigorous definition of the participation ratio that we use in the following. So actually, it is defined with the local density of states in this way. And imagine that you know the scaling exponent xq of the critical density of state power q averaged. Then you can simply extract the multifractal exponent, which is xq minus qx1. So basically, this tells you that the multifractal exponent extracts the nonlinear part of the scaling dimension of this quantity. Before going to the following on the discussion with the moments of density of state, I'd just like to draw your attention to the scalings of these moments at the thermodynamic limit for q bigger than 1 in this case, and compare it with Anderson localization. Because you know that for Anderson localization, you have a transition from extended states basically to localized states, and both participation ratio and inverse participation ratio can pinpoint the transition. Because for localized eigenstates, the inverse participation ratio is non-zero, whereas the fraction of site occupied is 0, so that the participation ratio vanishes. And conversely, for the extended phase, whereas in the case of the semimetal-metal transition, what you have is that on the semimetal phase, basically nothing happens because there are no eigenstates at 0 energy. While on the metal phase, only the participation ratio is non-zero. So this is the reason why I define the multifractal spectrum through this participation ratio, because it is actually a better indicator of the transition for the semimetal-metal transition. So now I would like to show you how very simply you can find the behavior of the typical density of states. To do that, I will use this handy function, which is the singularity spectrum, that I define here for the normalized density of states, which is basically the density of states divided by the average of the density of states. So I define this density as some exponent of the size of the system, so L power minus alpha, and then I write the probability distribution of the exponent alpha also as a power law, as a power of the system size, so L power g of alpha. And this g of alpha is called the singularity spectrum, which is, I remind you, defined here for the normalized density of states, so it's a bit different than the f of alpha that you are used to, but it's very closely related actually. And so basically g of alpha gives you the probability distribution of the density of state, but in a log-log scale, basically. And simply using the scaling of the Q power of the density of state, and using the steepest descent method, you can show that this function g of alpha is simply the Legendre transform of the multifractal spectrum. Typically, this is at criticality, this is a convex function, approximately parabolic, and whose maximum is 0, and which peaks at some value that I write as alpha naught minus dimension d, where alpha naught is the most probable exponent for the scaling of the density of state. Now, simply using the definition of the typical density of state, which is the exponential of the average of the log, you get this universal scaling relation, which is that rho typical divided by rho average scales as L power d minus alpha naught. So let's apply these scaling relations to the two transitions that I want to study here. So the well-known Anderson localization, in this case, the average density of states varies smoothly across the critical point. So formally, the corresponding scaling exponent beta is 0. And applying this relation, you get that this famous result that beta t, so the exponent for the typical density of state, is nu times alpha naught minus d. Now, if you apply this relation for the semimetal-metal transition, here it's a bit different because, of course, the average density of state vanishes on the semimetal phase. So it has a non-trivial exponent, nu d minus z for the scaling law. And then you get that the typical density of state also decays, but with an exponent nu alpha naught minus z. Okay, so now let's go to, the more technical part, which is how you can compute the multifractal spectrum to deduce alpha naught, for instance. So I describe the semimetal phase, the system, by an action in 3 plus 1 dimensional. So it's a quantum field theory for a single Y node. So there are two Grassmann fields, psi and psi dagger. Then I average this action. So to do that, thank you. There are several tricks. The one that I use is the replica trick. So basically, I introduce n replicas of the system with n integer, and I'll continue analytically the result for n tending towards 0. The average, after averaging, you get this active action, which is which contains this first part, which is the free part, actually. So recognize the free Hamiltonian. And you see that disorder generates this effective, attractive quartic fermionic interaction, whose coupling constant is basically the disorder strength. So I consider the general case with short-range and long-range correlations for disorder, here written in Fourier space. Then, of course, you have to deduce the transition, so the fixed point. You compute the beta functions and study the renormalization flow of these two coupling constants. So this is represented here below. You have to distinguish the two cases, the first case being A bigger than D. So in this case, you see that, on the left you have the white metal phase, which is the basin of attraction of the Gaussian fixed point here. On the right, sorry, you have the metal phase with the disorder strength going towards infinity, and between you have this critical line which flows towards this relevant fixed point. So in this case, the fixed point is for a non-zero value of delta S, short range, but a 0 value of delta long range. So basically, this is the short range control transition that was already studied by Eduardo Fradkin. But in the case A between 2 and D, this fixed point becomes irrelevant, and another fixed point appears with a non-zero value of delta L. So the critical exponent here will be different and controlled by long-range correlation of disorder. So this is basically another universality class for the transition. Now, remember that I want to compute the scaling exponent of the power q of the density of state. To do that in the replica trick, it is actually represented by this composite operator, which is simply a product of the wave function density over q distinct replicas. Then I compute xq at 2 loop, and I deduce the multifractal spectrum in 2 plus epsilon dimension and A equals 2 plus delta regularization. So the results are the following. Consider the short range controlled transition, so for A bigger than D. You obtain this value of the multifractal exponent, which is quadratic in Q and of order epsilon squared. You see also that it is negative as it should be. And this exponent was actually already computed by Cizanov, but using a supersymmetry technique. Now, in the case of the long control transition, you have basically the same form of delta Q, except that it depends on both epsilon and delta. And so you see that for A equals 2, that is delta equals 0, which corresponds to the critical line for the Harris criterion, the multifractal spectrum vanishes, which is consistent with the fact that actually the transition disappears and that the white metal phase is always driven to the metal phase. Let's compare it with first Anderson localization. So for instance, consider the orthogonal class in 2 plus epsilon dimension. So the first part, the quadratic part, you see here is of order epsilon, and what is more, the factor in front is 1 instead of 3, 8. So generally speaking, the multifractality at the Anderson localization is a bit stronger than at the white metal-metal transition. And there are also numerics that have been done on the white metal-metal transition, but only for short-range correlation. For instance, this work by Pixie and collaborators, where they nicely track the average and typical density of states. So they deduce these exponents beta and beta typical, and from these exponents we compute alpha naught, which is 3.7, which is in quite good agreement with our analytical result, which is 3.6 using Padé resummation. Of course, we have also computed the alpha naught for the long-range correlated case, but I'm not aware of any numerical studies studying these long-range correlations. So the take-home message, I think, is that multifractality is weaker at the semimetal-metal transition than at other sound localization in general for localization to adjacent, and it is even weaker when long-range correlations control disorder. So I think I have to finish, so I just show you these perspectives for a continuation of my work, and I would like to thank my collaborators at the Laboratory of Physics, so Andrei Fedorenko, David Carpentier, and Thibault Louvet, and I thank you for your attention. Yeah, sure.